Okay, 2.1 notes. This is over function, so let's start with some function notation. So let's say we are given a function. Let f of x equals 3, let f of x equals 3x squared plus x minus 5. This is function notation, just like y equals, we've been over this. And let's do an example where we say find f of -2. Now remember, this is not multiplying the function by -2, it's replacing the x with the -2. Okay, so we just plug in -2 everywhere there's an x, and you should be able to do this without a calculator, even if -2 happens to be a fraction in another problem. You still should be able to do this without a calculator. Okay, so we have 4 times 3 excuse me equals 12, and then we have minus 2 minus 5, and that is equal to 5. Okay, good. All right, on another problem, this should all be review, we might have f of a. Now, we've seen this in after parties, and you've seen this in Algebra 2. This is even easier. This is just 3a squared plus a minus 5. The reason I say it's easier is because there's nothing to combine. That is your answer right here. Okay, let's say that we want to do f of a plus 2. Well, we approach it the same way. We plug in this new input, which is a plus 2, everywhere there is an x, and then we simplify it using all those good simplification skills we practiced last chapter. Okay, this needs to be a plus 2 times a plus 2. Okay, so if you were to multiply a plus 2 times a plus 2, you would have a squared plus 2x plus 2x, or 2a, which would be a combined of 4a, and then plus 4. And then we have plus a, that's going to be minus 3. Okay, here we have 3a squared plus 12a, I'm just distributing the 3, plus 12 plus a minus 3. And so in total, that would be 3, my pen is not cooperating with me today, 3a squared, and then plus 13a plus 9. And there are many other types of examples we could give from there, but I think that's enough practice. Okay, let's do a different type. Move this up. We're still using the same function, but this time let's do 2 times f of x. Now this 2 is what we sometimes call a scalar. It is a multiplication. We're not plugging anything in for x, we're multiplying the whole function times 2. And so we would distribute, we would have 6x squared plus 2x minus 10, and that's it. You don't need to factor any of these unless it says to factor. Okay, and then the last one we're going to focus on is something that is on your after party, but I wanted to put it at least in the notes as well to make sure that everybody's got it. Okay, and that is this whole notion of f of a plus h minus f of a all over h. This is not going away. This is not something that's made just to make your life more difficult. It is something that you really should be able to do. It's important in calculus. We will talk later about what the importance is, but it has to do with something called the derivative. Now, we're plugging in a plus h in for x, so we'd have 3a plus h squared plus a plus h minus 5. And since I'm subtracting something that's more than just one term, I'm going to use parentheses. And then 3a squared plus a minus 5. This is all over h. Okay, so then we need to FOIL the a plus h and multiply by 3. I'm going to do that all in one turn. If you need to do that in multiple steps, that's totally fine. And then we have plus a plus h minus 5 again. And then this minus distributes. Now, always when you're doing these problems, lots of things should cancel. Okay, if they don't, then you messed up somewhere. So like here, these 5's cancel, these a's cancel, and these 3a squareds cancel. And what you have left, if you notice, the 3 things left all have an h in them. So I'm going to factor out an h, and I get 6a plus 3h, and this last term would be plus 1, all over h. We have a cancellation there, and our final answer is 6a plus 3h plus 1. Now, if you've already done your after party, then you know that if you let h be equal to 0, you can see that the 6a plus 1 has significance, and that is all stuff we're going to explore throughout the semester. Okay, let's just start with piecewise functions. We're not going to do a whole bunch with them, but let's do at least one example, and we're not going to graph today. We're just going to talk about what they are. Okay. And so let's use a new function. This time we're going to use g of x, and that's going to be equal to x squared when x is less than 0, and it'll be equal to x plus 5 when x is greater than or equal to 0. Okay, and there's a couple different things I could ask you from here, but they'll be similar using function notation. So let's use g of 2 first. You don't want to plug it into both. You want to look up here and decide which one does this fit into. This x value of 2 is greater than or equal to 0, so you want to use the second equation. So 2 plus 5, and that's going to be equal to 7. All right, let's say I gave you g of negative 3. Well, then that number is less than 0, so you'd use the first one. So you'd have negative 3. Now remember, when you're squaring a negative number, you square everything, so you get 9. Let's do one more. Let's do g of 0. Now this is where you have to look closely at the inequality, and then this tells me that 0 would be included with the second one, so 0 plus 5 is 5. Okay, let's talk just for a little bit about domain. Domain is a word you should be very comfortable with. You've seen it, we've practiced it, although what I really want to focus on is the 3 functions where domain is kind of wacky. Okay, that's y equals square root of x, y equals 1 over x, and y equals, we can either say log x or natural log x. Both of these have the same domain. All right, now what makes the domain of square root of x weird? Well, it's the fact that you square rooting in a negative gives you imaginary or complex numbers. So for this parent function, our domain is x greater than or equal to 0, or you could say it's from 0 to infinity. Now that will change as the argument changes, but this is where you want to start. For the second one, for the rational, we don't want x to be 0. So in interval notation, that's going to be negative infinity to 0, and we're going to union that with 0 to infinity. Basically, all the numbers less than 0, all the numbers greater than 0, and this will change as the denominator changes. Again, okay, with log, you may not remember this one as much. You have to take log of positive numbers. You cannot take log of negative numbers or even 0. There is an asymptote on the line x equals 0, the vertical axis. So you want x to be greater than 0, which would be parentheses 0 to infinity. Okay, now if you remember these basic concepts, then any other problems I'm going to throw at you, you should be able to reason through. So like for instance, let's say we have f of x equaling to 1 over x squared minus x. Now this fits into the second category, rationals. The first thing you really want to do is factor this, 1 over x, x minus 1. And there are two numbers that cause me to divide by 0, or they cause vertical asymptotes, in that we don't want x to be equal to 0, and we don't want x to be equal to 1. I was looking at the denominator for that. So let's write an interval that skips these numbers. So we start at negative infinity, and we first skip 0, and then we use all the numbers between 0 and 1. Those are fine. We got to skip 1, and then all the numbers greater than 1. Those are all included in our domain. Now the range on a lot of these is a little bit more difficult, so we're just going to focus on domain for right now. Okay, let's do another one. Let's say we have f of x is equal to the square root of 2x minus 3. Okay, this is like the top one. This is where we want our argument, what we're taking square root of, to be greater than or equal to 0. So let's set up that inequality. And we just practiced in the last unit about solving inequalities, so you should be really good at this. Add the 3 over. Now we've got 2x greater than or equal to 3. So our domain is x greater than or equal to 3/2. And to write that as a interval, we would do bracket 3/2 to infinity. And one thing you would want to be careful on these square roots is anytime you divide or multiply by a negative, you would switch that inequality symbol. Okay, let's do another one. Let's say this time we had h of t is equal to t over the square root of 1 minus t. This is kind of combining both aspects. On one hand, we've got 1 minus t cannot be 0. Okay? On another hand, we've got 1 minus t would have to be greater than or equal to 0. Now I'm going to, in combining this, okay, what takes care of that first part is if you just do a greater than 0 instead of a greater than or equal to 0. Okay? So now let's solve for t. So if I subtract 1, I have negative t greater than negative 1. If I divide by a negative, remember that switches that inequality around. So my domain is going to be negative infinity to 1. So that's kind of combining a and b. Okay, one more example. Let's say we have f of x is equal to the square root of x squared minus 2x. So again, you set the argument, what you're taking square root of, greater than or equal to 0, because we know that has to be true, and now this is a quadratic inequality. Now remember, we solve these by factoring. Okay, our two test points are going to be 0 and 2, so we plot those on a number line. And you can either think of that, since these are solutions to the equation, they have to be solutions to the inequality. You can either think of the parabola being drawn, and where is this parabola greater than or equal to 0, or you can do test points. And so where is this parabola greater than or equal to 0? It's on the outside. And if you had done test points, you would have gotten the same value. So after we solve that inequality, we now know our domain for our original function is negative infinity to 0, bracket, and 2 to infinity. Now there are many other types, and we didn't do a practice on a logarithm. That'll come later. But there are even more complicated ones than this, and so we're just going to take them as they come. Okay, please bring your questions to class.